So there is a really interesting question that everybody should ask. It's a really hard question to answer, but it's perhaps the most important question to ask of yourself, and it's this: what would be amazing? There's this lovely expression from, I think, Wayne Gretzky in ice hockey, who said, you miss 100% of the shots you never take, right? And in a sense, any kind of field game is easy because you know where the goal is, right? But this question, what would be amazing, is really hard because you don't know where the goal is, right? And you have to think about, like, what would be amazing? This is the sort of question that a child asks themselves without realizing you're supposed to have permission to ask that sort of disruptive question, right? But asking that question is the only way to figure out where the goal is to take the shot. So I remember about 30 years ago saving up student money to go and buy some software. It took me about 6 months. And what I was interested in was small talk, right? And I remember, as a kid at the tip of Africa, just thinking, wow, I am never going to catch up. Never going to catch up. Because if it takes me 6 months just to figure out small talk, how am I going to get to play with all the good stuff? And of course, it wasn't long after that I discovered open source. And suddenly the whole world changed. And I think there are probably people in this room who had a similar experience, right? Suddenly everything was amazing, right? You suddenly had access to great stuff everywhere. And if I look back over the last 30 years, it really is true that we have leveled the technology playing field, right? If you're a kid in California or a kid in Karnataka, you can sit down at a Raspberry Pi and you can play with the very same stuff that a Google engineer is working to build the Google future on, and you can build your future on exactly the same stuff. And that's really like what gets me up and into the office every single day, right? That central idea. We've moved from a state of kind of scarcity of software to this amazing state of abundance. And that's great, but of course, it changes the problems. Right? And so the problem today isn't access to software, it's managing it. It's knowing what you've got. It's knowing what state it's in, right? People in this room, you can probably relate to having thousands of Docker containers built by other people, right? And somebody asking you a question, are they healthy? Are they good? Do they meet our requirements, right? And in a very interesting way, that is now the problem, right? It's not, can I get access to technology? Yeah, you can get access to technology from Goldman Sachs in this forum. You can get access to technology from Google, from Microsoft, from Oracle before anybody else gets it, right? That's incredible. Now we have to manage it. So I wanted to talk this morning about something that I hope you will find amazing. And I call it everything LTS. Now, some of you may know that the term LTS was coined about 18 years ago with the release of Ubuntu 6.06 LTS. And now that it's 18 years old and a grown-up adult, I can tell you that it was conceived in London. And like many London ideas, it was conceived in a pub on a Friday night, the Admiral Codrington in Mossop Street. So there probably should be a rule against naming products in a pub on a Friday night. But anyway, here we are 20 years later, and this term LTS has gotten quite widely adopted. Now, in Ubuntu, as a kind of challenger outsider distro, we had a reputation for really focusing on developers who wanted the latest stuff, and they wanted it quickly in an easy-to-use form. And what we were trying to do is connect that audience to the audience of people who need to deploy stuff and run it for a long time. And so LTS really means that commitment to a long time, and over time it's grown to mean HIPAA, SOX, FIPS, now the EU CRA, the FCC cyber trust mark, compliance of that great big pile of open source with those complex sets of requirements that your developers don't necessarily care about, but your institution does and should. And over the years, we grew the Ubuntu LTS commitment until, I think 2 years ago, we announced it would cover 35,000 source packages in Ubuntu, the entirety of Ubuntu, the biggest collection of software on the planet. And we were kind of proud about that, right? Now, finally, your kid in Karnataka could build stuff and put it into production on literally exactly the same platform that was being used inside the biggest companies in the world, the wealthiest companies in the world, right? I was proud about that until I went to see the CISO of one of the world's biggest companies, and they said, listen, it's great, it's excellent, I really appreciate it. Thank you for scratching the surface. I'm like, well, what do you mean? And they said, well, let me show you what a Docker image looks like in this building, right? He said, I've got hundreds of teams, and they're all building on Ubuntu, and it's brilliant now that their app is sitting on Ubuntu Pro. Everything in there is maintained, well done. He said, but look at this. I've got piles and piles of upstream code, which we have to have. It's brilliant stuff. It's the latest stuff. It's what the developers want, right? And there's no LTS. So that was a bit of a shock, right? When we went and looked at it, we had 35,000 pieces of software that we've figured out how to cover. When you go and look at GitHub, you're closer to 300,000 pieces of software. And if you survey a bunch of organizations, you will easily find 150,000 pieces of software that are in production use from various Git places, GitLabs, GitHubs, Git places. So back to the drawing board. What would be amazing? So I don't think we would have solved this problem for anybody unless two very large organizations, one a very large silicon company and the other a very large public cloud, both came to us with essentially the same request at exactly the same time. And that was, they said, look, we have hundreds of teams and they're all using Ubuntu, and it's very nice that you've scratched the surface, but we literally have 6,000 pieces of Python and related software that we're using to build ML solutions for, and we have to be compliant, and our engineers cost $300,000 a year. And so working with those organizations, right, we try to answer this question. What if you could get every single one of those upstream pieces of software as an LTS? And for those organizations now, that's in production. So for those organizations now, they take their base images, which they craft on a standard distro environment, maintained packages. They then essentially use a set of repositories, internal repositories, which have LTS maintained versions of the upstreams that they need, right? And they build their Docker images out of that. And they have a 12-year LTS commitment to that entire stack. And today, what we're in a position to do is offer that to any organization that's building on top of open source. It's a pretty straightforward process. Typically, that organization has clusters of Docker images because they have clusters of stacks, the Java stack, your Python stack, your ML stack. When you look at your Docker images, you'll see that they may vary quite widely, but you can organize them into groups. And often those groups of Docker images share dependencies. They share piles of things that developers have agreed to use because one developer told another developer that it was good. And that analysis can be quite time-consuming. It's a bunch of work to climb in and look at that. And often there's opportunities when you're doing that analysis kind of as an external party to find kind of commonalities. So it turns out you don't need version 1.5, 1.6, and 1.7 of some YAML processing library. It turns out that you could build all of those containers with one of those. So you can reduce the total number of external upstream dependencies. And it may be that a bunch of those dependencies are already dependencies that we have under an LTS maintenance commitment, right? Typically, that's not the whole story. Typically, there are some things that each institution is using that they've selected for whatever reason, or which they have open sourced, which aren't already effectively under that LTS umbrella. So we'll then onboard those dependencies, make the 12+ year LTS CVE maintenance commitment to those dependencies as well as the existing ones. Everybody else then gets access to those new packages, not packages, those new upstreams effectively, in a standardized format, right? Then go through a process to design containers. Now, why design containers? You've already got containers. But it turns out the container production process is kind of messy. And the way you make containers often has grown organically. Right? People essentially, there's a very nice experience you get with Docker that you can essentially try something, codify that, try something else, codify that, try something else, codify that. Often going back and looking with fresh eyes at that set of containers lets you rationalize things and clean them up. And that's quite important from a security point of view, because in that process you're essentially simplifying, reducing your attack surface, and making some decisions about what you want your attack surface really to be, right? And on all of that, we will then make a 12-year LTS commitment to that custom stack, right? What we've seen is that in certain domains, there's actually a lot of commonality between businesses in the same industry. So if I take those two separate requests for piles of Python to support AI/ML, in fact, there was a lot of commonality, and it was possible to rationalize between those organizations without them having to know too much about each other's business. To rationalize that dependency tree, because some of those dependencies nobody cares about. As long as there's a version there that works and it's compliant, nobody cares about the difference between version 1.5 and 1.6, right? So at this stage, it's a conference in 2024, so we have to talk about AI. Two of the biggest clusters in that ML stack are PyTorch and TensorFlow, and optimized versions of that for GPUs and specialized silicon of various forms, and about 2,000 further dependencies that are directly related to that core stack, right? And the interesting thing about that stack is that it is almost certainly never going to make it into a distribution. It's moving too fast, and the nature of those packages is such that it is almost certainly never going to make it through the traditional packaging process. It's almost like in the Git world, we have broken the packaging sound barrier, and new pieces of content are being created upstream far faster than they can make it into any of the existing enterprise distributions, right? The process of integrating those pieces of software is slower. And part of the reason for that is that at the package level, what a distribution does is it tries to make sure that everything can live in the same file system with everything else. And containers have changed our need for that. You no longer need to be able to have everything that's in the distro installable at the same time, effectively, because you're typically building standalone containers. And if the contents of one container would clash with the contents of a different container, it doesn't matter, because containers. So that we thought was brilliant, until one of those companies came back and said, here's a curveball for you. We're making all of the software. We're shipping it as Docker images. People are very happy that it's compliant, but they want to know if you'll support it on some other Linux distro. And so we will. We'll support each of these containers on Ubuntu, obviously, on VMware, on RHEL, and on any of the major public cloud Kubernetes infrastructures, so AKS, EKS, GKE, OpenShift, Tanzu Kubernetes Grid, the VMware Photon based Kubernetes, all of those are fully supported. So now, I hope we can really LTS everything for any organization, regardless of their fundamental choice in infrastructure. We do see in most organizations, they will have a pretty rigorous policy about what they want to run on the metal and why they want to run that on the metal. But they are able to consume Docker images, right, from vendors, as long as those Docker images meet their certification, compliance, conformance requirements, HIPAA, SOX, FIPS, and so on, right? So I believe now any developer anywhere on the planet has a path to build on the latest and greatest open source and then ship that software into any organization, telco, government organization, public sector, finance sector, and be able to meet 10+ year certification and conformance requirements. And we will do the work, the lead bullets rather than the silver bullets. We will do the work to maintain that. Each additional piece that we onboard into that collection is immediately available to be used in the Docker images of other organizations. So this becomes the world's largest shared set of software that is under an LTS commitment together with a Docker image delivery capability. So about those Docker images. Now, I think someone pointy said I needed to call them OCI images because apparently they're OCI images. Everyone I know calls them Docker images. You know what I mean. What would be amazing? If you go and look at collections of Docker images, they're messy, right? That culture, that convention is so free-form and exploded so quickly that if you look at Docker Hub, it's hard to see the patterns, right? You've got lots and lots and lots of different ways to think about a Docker image. So in the process of doing this, because we were passing Docker images between people and building Docker images that people would pass between themselves inside an organization, we focused on a couple of key things, still Docker images, but key conventions that really simplify and improve the experience of working with other people's Docker images. The first, obviously, is to make these scannable in a much more rigorous way. Scanning Docker images is heuristics. And too often, you're in a situation where you're getting too many false positives to really be confident in the state of your container estate, right? So how do we fix that? Well, by working directly with Google, for example, on OSV, or with Qualys, Tenable, Rapid7, and some other vendors, we can send them not just package names, which is conventionally what they would look at. In a well-designed package, in a well-designed container, you may not have package names. Actually, the signatures of individual files of different generations to be able to tell exactly what's in that container with super high precision. So very easily scannable containers. Standardized, I would call them behaviors, right? Standardized entry points. One of the things I think in the haste of the kind of Docker community is it's very difficult to introspect a Docker image from inside the Docker image, right? Because different pieces of information are provided to the container runtime, Kubernetes, whatever, and the container itself. So by creating a standardized entry point, in other words, by saying, look, every single one of these containers runs exactly the same supervisor, that's the first thing it runs. So it's a tiny little piece of code, right? But it's exactly the same piece of code. And then what's actually going to be run by that is configuration inside the container. And the interesting thing that that does is it lets you introspect from inside the container what's supposed to be going on. It makes for much simpler deployment and integration when you're working with lots of different containers from lots of different teams. It addresses, one of the kind of key stress points between the dogma of containers and the reality of containers. The dogma of containers, the ideology, the rallying call was, hey, let's just put a single application in a single container, and then we've got one simple small thing that we can deploy anywhere. The reality is you have different concerns in an organization, the CISO, other groups, developers, and they all want slightly different things, and it's quite hard to compose those things. But if you can essentially say, look, every single container can have a manifest of services that are available in that container, and we can then turn those on and off, right? You can essentially integrate the different needs of different groups inside the same organization without driving everyone completely insane, right? You can also move some of the intelligence about health and some of your logic about how to respond to things that happen in production or at runtime, you can move those into the container itself. So, if you've got a tree of processes in a container and one of them dies, the dogma is, well, tear down the whole container and run it again, maybe on another machine, because Kubernetes. It turns out often that's not what you want. Often you want the ability to have a small amount of logic that says, well, actually, I'm fine, I'm just going to restart that thing, right? Or sometimes you say, no, this is fatal, right? Put up the red flag, call the fire brigade, this is absolutely fatal. And that logic is hard to encode on the other side of Kubernetes, right? Because on the other side of Kubernetes, if you're outside of your container orchestration environment, and you're looking at that, you just don't have a very clean line of communication. If you shift some of that logic inside the container, you can deal with those circumstances and services, right, inside the container. You still can send your red flag out to Kubernetes or whatever's kind of looking at that service from a distance, but you can do much more agile response inside the container. And perhaps more importantly, you can test that because you have that anywhere you have the container. It's now just logic that goes with that set of services in that container. It's part of the artifact. You can take that to a dev environment and you can check that your logic is good. You can put that in staging. You can check that your logic is good. If you're doing that from a distance, then you usually end up having some other piece of logic somewhere else, and usually you have different people looking after that logic, and it's all very messy. So this is nice and contained and tight. Part of that is kind of understanding the way Docker allows people to build on the work of others. The layering structure of an OCI image is deliberate, right? You can take a container and then say, oh, I want to take that container, I want to add some files, I want to change some files in my layer, and then you can build up another layer. One challenge is that adding and removing piece is a little bit ugly. You can never really remove something, right? You can say, pretend it's not there. And you can't really modify something in place, right? You can replace it. Now, what that means is that if you have these different concerns, you have the SecOps group, and they have some things they care about, and you have another group, and they have some things that they care about. If this one has to overwrite this one's file, it's hard for this one to kind of express a policy that doesn't just simply get slammed, right? So, for example, if you have layer-friendly config, you can say, look, this base layer has its own config. Your config is another file right next to that, which you can inject in your layer. And that layer can essentially say, I don't want to run this service from the base layer, or I want to modify that service, right? But if the base layer changes and adds another service, I have no opinion. And so again, you can have this much more reasonable separation of concerns, different teams responsible for different things, with a much more reasonable way of working together. the Google characters came along with a very cheeky term, and they said, we want you to make distroless containers. And at first I thought they were being rude. You know, we're a distro. What do you mean you want distroless containers? And what they said was, look, the attack surface of a container, right, is much worse if you have all sorts of other utilities and files in that container. What we want are containers that only have the files needed to run that application. So we're thinking, well, how do we do that? And then some other people from the same organization came along and said, don't do that, right? The problem is we hate those containers because when something's broken in there, we're dead. We have nothing to help us debug in that environment, right? Don't tell them we said that. What do we do? So we're really inspired by a famous line that is probably attributed to the wrong person. So the story goes that Michelangelo, someone asked Michelangelo, how do you create something so beautiful out of this lump of rock? To which, allegedly, he said, the statue was already there. I just had to remove what you didn't want. And so we built a tool called Chisel that lets you take a standard distro full image and essentially declare what you want in the statue that's going to remain. So you can use essentially exactly the same recipe, and you can build an image that has all of those janky things that are a bit of an awkward attack surface, but developers love, or just the product artifact, which the CISO is going to like, which is the distroless artifact. It has none of the distro metadata and extraneous files and so on. It's smaller and nicer. So the tool that we build these containers with is, because of that story, called Rockcraft. And if you hear us talking about rocks, they're just Docker images. They're just Open Container Initiative images. But because we use Rockcraft, they all have that standard entry point. They all have the set of behaviors that I've been describing. Now, we're about to run out of time, so I want to try and get a little bit nerdy and show you a little demo of code that I think changed last night. What could go wrong? Lots of people are super familiar with Docker images. They find they're super comfortable with them. They know exactly what's going on. They can write them they can write bash scripts to make Docker images. There are also great developers who aren't, right? Maybe you're just a Python developer and you've just been asked to build Flask applications. So how can Rockcraft help you? So inside Rockcraft, there's an extension mechanism, and we can create extensions, anyone can create extensions, that understand essentially all the things that you need to have in a Docker image to support a particular outcome, particular kind of outcome, right? So let me switch to a tab. Can you see that? So I have here the world's simplest Python Flask application, hello world. And I also have a requirements.txt, which is the standard thing that says, hey, use Python, go fetch Flask. And that's it. So I want to say, what extensions are in my Rockcraft? I've got this Flask framework extension here, so I'm going to say Rockcraft. And I get a single file, a Rockcraft metadata file. And that's pretty simple. But the things I want you to pay attention to are, it's got a version, it's got a base. So this is saying, build me a Docker image on Ubuntu 22.04. And it's got this Flask framework. And that's it. Pretty much everything else is either a comment or commented out. If I ask Rockcraft to expand that, what that Flask framework did, you can tell me, you can see that it's added a whole bunch of stuff. That's all the stuff that you don't need to worry about, or you don't want your Python Flask developer to have to worry about. And basically what that's saying is, hey, we're going to want to install a bunch of packages in this Ubuntu 22.04. We want Unicorn, we want Python 3, and then we're going to essentially take that Flask app, Python, stick it in the Docker container. Oh, we'll add some statsd and Pebble, which is that standardized entry point supervisor. So I've just got those 3 files, and if I say Rockcraft pack, it's going to go off and make me a Docker image. And one of the nice things about this is the Docker images that Rockcraft makes are kind of like ISV artifacts. There's a difference between the stuff you get when you're hacking at things for yourself and kind of iterating, and the stuff that you're comfortable shipping as an ISV. So when you're iterating, you tend to leave a trail behind of your thought process, your workings. And when you're an ISV, you kind of want to present a pristine image. You get a similar problem with Packer, for example, like where it says, take a standard image, boot it, do some stuff, shrink wrap it. And the booting process and the do some stuff process tend to leave residue. And we want to build images that have no residue at all. In the background, it's used LXC to spin up a clean machine, and all of the build and packing happens in that clean machine. So there's no way for taint on my laptop to effectively dribble into and all over that Docker image. And I now have a 65 meg Docker image. But I told you about Chisel. So if I go in and change that and say, look, I wanted to build on Ubuntu 24, but I want a bare base image. That's like saying in the Docker build story from scratch, right? I want a bare base image, and I think I'm going to change the version number. And then I'm just going to pack it again. Let me go over. Let me expand the extension again, and I'll show you what it's done differently. Instead of saying it just wants a normal package, it's asking for a slice of that package. The way Chisel works is there's a little database of slices of the underlying distro packages. And so what we're saying is this slice is in the statue, everything else isn't. And slices can have dependencies. So just by specifying the leaf slices that you want, you essentially specify the outside of your statue. And that's how we chisel the image. And if I go back here, you've got a version 2, which has shrunk by 20 meg. So we're now down to a 43 meg Python Flask Docker image. Now, I would love to show you that running, but I've got a red clock over here, so I think we're out of time. Thank you very much.